Hello everyone, today we're going to continue talking about second order systems with a little bit of repetition from last class. So, just because I know that you could just watch the video again, but just to explain it in a different way, see if it matches this time. So, second order systems continued. Last class we talked about the fact that you could have a transfer function that is represented in the format of a omega n squared over s squared plus 2 zeta omega n s plus omega n squared. And if we, if we want to, we could have a system in state space. If we took the eigenvalues of our A matrix, then we would have our poles in the format of the solutions of our characteristic equation. So if we do the quadratic equation, that would be negative zeta omega n plus or minus the square root of zeta omega n minus omega n squared. Actually, zeta squared omega n squared. So we could also make this negative zeta omega n plus or minus, let's go ahead, erase this, omega n times the square root of zeta squared minus 1. Now, if we know that zeta is less than 1, then we're going to have an imaginary number there. In which case we could say it's negative zeta omega n plus or minus j times omega n, and in doing so we would take a negative 1 out of our equation, which would flip these two signs, 1 minus zeta squared. And those two equations are equal to each other, the one in purple and the second one in blue. We just tend to use one if we're having an overdamped system versus an underdamped system, but they are equivalent. So if we have a system and we find out that our poles give us real and imaginary components, then in the response to a step function would be a system that oscillates and eventually reaches equilibrium. And we could draw a little envelope around that. And that envelope, the time it takes to reach that equilibrium is determined by the settling time of our whole function. So the smaller the tau is, the faster it will take to reach equilibrium. Now, if we have an overdamped system, that's going to be one where we have two real poles, and the poles are unique, they don't overlap. So we have that zeta is greater than 1. Then we can have a system that will look a lot more like a first order system, and but it might be slower or faster. In this case, this one should be slower than the way that I drew it. Let's see if it lets me erase this. I'm going to make my life easier, and we'll draw the same squiggly line. Looks so nice before. Maybe it looked adequate before. So if we have it that the tau stays roughly the same, then we could just draw it as going the same way. And that would be a situation where zeta is greater than 1. The other one is underdamped, so zeta is between 1 and 0. So if we ever want to graph our poles, that's what I've done in the graph you see on the far left, where we have a real and an imaginary axis, and we take the imaginary component and graph it vertically, the real component and graph it horizontally. So let's say that we have a system where we have poles at negative zeta omega n, and we're going to make it an underdamped system. Plus or minus j times omega n square root of 1 minus zeta squared. Now, if we want to plot these, the way that we would plot these is we'd have our real and our imaginary axis. No. Okay, my pencil's back working. So we have our real and our imaginary axis. We're going to post this at the negative zeta omega n is the real component of our poles. And we have imaginary components at plus or minus j times omega n times 1 minus zeta squared. Last class we also referred to this as omega d, and we can go ahead and write this as j times omega d. So if we plot these, we have these two components that have the complex nature, so we see them floating in the left-hand side of the plane. Because they're on the left-hand side of the plane, we can say that they are stable. If they were on the right-hand side, they would be unstable, and if they were on that imaginary axis, they would be a neutrally stable set of poles. But here we have stable, underdamped poles, and there's a couple neat things that happen if we graph it. So one thing that is nice is that if we take the hypotenuse, then we end up with 5 as, we don't end up with 5, we end up with omega n as the length of the hypotenuse. We have that omega d is the height, and zeta omega n is the length of that leg. So that tells us that cosine of theta sorry for the technical difficulties. So if we look at the angle at this line of the hypotenuse over the origin, so drawing a little vector from the origin to our poles, we can say cosine times theta, where theta is the angle between the real axis and the hypotenuse that leads to our poles, is going to be equal to zeta. So that's a nice way to kind of have a way to connect what's going on with your poles. We're going to do a couple of example problems in the Zoom meeting that kind of show how this works.